Welcome back to this video. In this video, we're going to solve this coding interview question, longest increasing subsequence. This is a famous dynamic programming coding interview questions. But in this video, we're going to solve these questions in n log n time complexity using binary search algorithm. First, let's talk about what is longest increasing subsequence. We know subsequence can be contiguous and it also can be non-contiguous. It don't have to be contiguous, but it can be contiguous, and the subsequence should maintain the relative order. In this given list of numbers, what is the longest increasing subsequence? The longest increasing subsequence is 2, 3, 7, 8. It also can be 2, 2, 3, 7, 101. So the longest increasing subsequence is 2, 3, 7, 18, not 8. It also can be 2, 3, 7, 101, 2, 3, 2, 3, 7, 18. We see that we have multiple longest increasing subsequence. We see that we can have multiple longest increasing subsequence. The length of longest increasing subsequence is 4. We have to return the length 4. We don't have to return the subsequence. We have to return just the length of the longest increasing subsequence. What is the longest increasing subsequence for this given list of numbers? That is 0, 1, 2, 3. 0, 1, 2, 3. The length is 4. The length is 4. We should return 4 for this given list of numbers. Now let's talk about how to solve this problem in log n time complexity using binary search algorithm. This solution is going to be a little bit tricky. Don't worry, watch this video till the end. Let's assume we're given this list of numbers. First thing, what I'm going to do, I'm going to create an empty list. We have empty list. So first we have 0. Our list is empty, so we will insert 0 into our list. Okay, we have 0 in our list. This is our list of length 1. At this point, we have included this 0. So this is our first step. In our list, we have just inserted 0. Now the length of our list is 1. Now let's move to the next element. That is 1. We see 1 is greater than the last element. Last element is 0. Remember that we will keep track the length of longest increasing subsequence. We will not keep track the longest increasing subsequence. The length of our list will tell us the length. That means the length of our list. The length of our list is the length of longest increasing subsequence. Now we have 1. We see the last element is 0. So here I'm going to insert 1. At this point, we saw that we have 0 and 1. Here we have 1. What it tells us? It tells us we have at least one element less than 1 on the left. It means that we have at least one element which is less than 1. It could be 0, it could be any other numbers. We don't know. Okay, just remember it. We have here 1. It means that we have on the left of 1 at least one element which is less than 1 and which is following the relative order. At this point we have 0 and 1, so nothing need to worry about it. Let's expand it. We have 0. Where we should insert 0? We cannot insert 0 right here. We cannot insert 0 right here. So what we can do, if we have 0, so we will run our binary search algorithms to this array. to this list, and we see we have 0 and 0. We'll just update this 0 with this 0. Okay, since we have this value 0 right here. Now what I'm going to do, I'm going to move to the next element. Let's move to next element. Now we see 3 is greater than the last element. The last element here we have 1. We see 3 is greater than 1. Here 1 tells us we have at least one element on the left of 1 which is less than 1, and also that element maintaining the relative orders. We don't know the element, but we have at least 1. Now we have 3, we can insert 3 here. We have inserted 3 here since 3 is greater than 1. Once we find out the current element is greater than the last element, we will insert that element. It means that we have at least 2 elements on the left of 3, who is we have at least 2 elements on the left. Those are less than 3, and those elements are maintaining the relative order of subsequence. Now let's move forward. We have 2. Now what I'm going to do, I am going to update the immediate next of 2. What is the immediate next of 2? That is 3. How we can find that? We can find that using binary search algorithm. We will see when we will implement our algorithm. So let's update the immediate next of 2. That is 3. The length of our longest increasing subsequence is still 3. Okay. After updating with 2, the length is 3. Now what this 2 tells us? This 2 tells us that we have at least 2 elements which is less than 2 on the left, and those elements are maintaining the relative orders. Here we have 1. It means that we have at least 1 element on the left which is less than 1 and maintaining the relative order. Okay, this is our core intuition. Now let's move to the next element, which is 3. Now here we had 3. If we do not update this 3 with the immediate next of 2 with this value 2, if we do not update this value 3 with this value 2, then on the right we cannot add this element 3. If we update this value 3 with this value 2, we can add the value that is greater than 2 on the right. That value is also greater than the value 3, the value we have just replaced or we just removed. Okay, we just updated the value 3 with the value 2. On the right we might have value that is greater than 3, and we might have the value that is greater than 2. If we find a value that is greater than 2, then we can add that on the right. But if we have here 3, we cannot add here 3. If we have this value 3 here, and if we have this value 3, we cannot add here 3. We cannot increase the length of our subsequence. Okay, so here let's remove this. Now we have 3. We see 3 is greater than 2. So let's update, let's just add this at the end here. Okay, we have 3. Now we are done. This 3 tells us we have on the left less than 3 by maintaining the relative order. Okay, on the left of 3 we have this 3 element. These 3 elements are maintaining the relative order, and these are less than 3, and these elements are less than 3. Okay, so we find out this array of length 4, or this list of length 4. The length is our answer. Length is the longest increasing subsequence, the length of longest increasing subsequence. But this is not our valid subsequence. This is not our valid subsequence. Okay, so this 0, this is our base case first. Then here we have 1. It means that we have at least 1 element on the left which is less than 1 by maintaining the relative order. Here we have 2. It means that we have two elements on the left which is maintaining the relative order and less than 2. On the left of 3 we have all element less than 3 and maintaining the relative order. We have at least the element 3 element on the left which is less than 3 and maintaining the relative order. Hope you have understood. Now let's take bigger example so you can understand this intuition. Now let's find out the length of longest increasing subsequence for this given array of integers. First thing, our list is empty, so let's add the first element. This is our first element. So at this point the length of our longest increasing subsequence is 2 for sure. Okay, now we have 1. Now our current element is 1. We see we cannot add 1 right here. 1 is not greater than the last element. So what I'm going to do, I'm going to update the immediate next of 1, that is 2. Let's update this value with 1. Why we're updating this value with 1? Let's think we have the value on the right which is greater than 2. If the value is greater than 2, that value also will be greater than 1, so we can update this value 2 with 1. Here our goal is to find out the length of longest increasing subsequence, not the longest increasing subsequence. So we are using this kind of techniques. Now we have 0. So what is the immediate next of 0? That is 1. Let's update this value with 0. Now you might think we have the value on the right of 0 which is greater than 1 and 2. If the value is greater than 1 or 2, that value also greater than 0, right? If the value is greater than 0 but not greater than 2 and 1, then we might lose the length of longest increasing subsequence because we will keep tracking the length by the length of our list. Okay, so let's move to the next. 5. We see 5 is greater than 0. 5 also greater than 1, also greater than 2. Also greater than 1, also greater than 2. So it's fine, we can add here 5. Now we have the last element 5. What it tells us that on the left of 5 we have at least one element which is less than 5. We saw that we have 3 separate elements which is less than 5. Let's think of, we have here element 1.5. The decimal number are not allowed, but just think we have here 1.5. If we have here 0 and 1, this is greater than 1 but not greater than 2. If we do not update this 2, if we keep this 2 right here, we cannot add this value right here. But we have the length of longest increasing subsequence is true, 1.5 or 0, 1.5. Now let's move forward. This is our current element 1. Okay, this is our current element 1. So let's update the immediate next of 1. What is the immediate next of 1? That is 5. So let's update this 5 with 1. What it tells us, this 1 tells us on the left of 1 we have at least one element which is less than 1. Okay, we have at least one element which is less than 1. We saw that we have at least one element, that is 0. This is not wrong. So we have updated this value 5 with 1 right here. Now you might think we might have here value which is greater than 6. We might have here 6, or we might have here let's assume we have here 4. We cannot add that. If we have here, if we keep here 5 and if we have here 1 4, then we cannot keep 1 4 here. We cannot keep here 4. Okay, we cannot add here 4. But if we have here 1, something like this, if we have here 4 and if we do not update this value 5 with 1, then we cannot add here 4 at the end, but its form 0 1 4 is a subsequence, right? So let's update this value here. Now we have 2. Now we have here 2. We see 2 is greater than the last element, so let's add here 2. Okay, so we have added here 2. We can add here 2, which 2 is greater than 1. Now let's move forward. We have 3. Before moving to the next element, what this 2 tells us? It tells us that on the left of 2 we have at least 2 elements which is less than 2, and they are maintaining the relative order. And we can say that we have 0 and 1 which is less than 2 and maintaining the relative order. That element can be 0, 1 or any or other elements, it doesn't matter, but we see we have a relative order, right? We might have here different elements, but this array will be in sorted order, so we can apply here binary search. Now we have here 3 is greater than 2, so we can add here. What it means that on the left of 3 we have at least 3 elements which is less than 3 and maintaining the relative orders. Since every single element maintaining the relative orders, so on the left of 3 all the elements will maintain the relative orders. Okay, now let's move to the next. 7 is greater than 3, so let's add here 7. What it tells us that on the left of 7 we have 4 elements. Those are less than 7 and maintaining the relative order. Every single element maintaining the relative orders. We don't know which are the element maintaining the relative order, but we have at least 4 elements. Those are maintaining the relative order, but we don't know the elements. If we know the element, then we can say this is a valid subsequence, but this is not a valid subsequence. Now let's move to the next. 11 is greater than 7, so let's add here 11. It tells us on the left of 11 we have at least 5 elements. Those are less than 11 and maintaining the relative order. Okay, since all the elements on the left maintaining the relative order, so 11 is also maintaining the order. Now we have 9. Now what I have to do, we have to update the immediate next of 9, that is 11, so let's update this with 9. If we do not update this, on the right we have 10. We cannot add here, but this is a part of a longest increasing subsequence. It might forms the longest increasing subsequence. Okay, we clearly saw that if we add here 10, it's from a longest increasing subsequence. If we do not update this value 11 with 9, then we cannot update that, right? So let's update this value with 9. Now 10 is greater than 9, so let's update here. So here this 9 tells us on the left of 9 we have at least 5 elements. Those are less than 9 and maintaining the relative order of subsequences. And here we have 10. On the left of 10 we have all the elements. Those are less than 10 and maintaining the relative order. Now we have 13. Let's add here 13 because 13 is greater than 10. Now we have 6. We have to update the immediate next of 6 with 6. So this 7 with 6. We're updating this because we might because at this point including this 6, at this point if we forget about on the right, including this 6 on the left, all the elements maintaining the relative order, and if we update this value 9, update this value 6 or the value 7 with 6, then it's no problem. This on the left of 13 we know that all elements are less than 13 and maintaining the relative order, right? So we can update this value. If we update this value, so we might have if we update this value on the left of 6, all the elements are less than 6, no problem at all. No problem at all, because on the left of 6 these 3 elements are less than 6. At least 4 elements on the left of 6 are less than 6 and maintaining the relative order. So we can do that, we can do just that, no problem. So including 6, if we includes this 6, then the longest increasing subsequence is this. So on the right we have 8, the immediate next of 8 is 9, so let's update this with 9. We have to update this value with 8 actually. Now we have 9, the immediate next of 9 is 10, let's update this value with 10. Same way, right? So similarly, then we have 12, let's update the value, the immediate next value of 10 of 12, that is 13, let's update here. And if we have a value of 14 here, then we can update the value right here, we can add the value right here. Okay, this is how this longest increasing subsequence algorithm works. This algorithm will take in log n time complexity. We have to apply binary search, that's why it takes a log n, and we have to iterate every single element of the given array, so it will take n, and we have to apply binary search, so it will take n times log n time complexity. This is how we can solve this problem. Hope you have understood the algorithms and the core intuitions of this algorithm. Hope you have understood this algorithm. Now let's implement the algorithm. Let's call the function length of LIS, longest increasing subsequence. Now here this function takes the given array, so nums array. Now what I'm going to do, I'm going to create a list. So list equals to this empty list, and I'm gonna add the first element to this list. So list dot add the first element into the list, so nums 0, the first element. So we're adding the first element to this list. Now let's run a for loop from the second element all the way to the end. So I equals to 1 while I is less than nums dot len I plus plus. This is our formal loop. Now here I'm going to check if our current element, so let's create a variable current equals to nums 0. If our current element is less than if our current element is greater than the last element of list, so if our current element is greater than the last element of the list, so list dot get the last element, so we can get using this function list dot size minus 1. If the last element is greater than if the last element is less than our current, then we'll add the current to our list. So list dot add current. Else, if not, if this is not true, what I'm going to do, I'm going to find out index. I'm going to call a function binary search. Binary search, this function will return the index. This function will update and return. This function will return the immediate next, the index of immediate next element of our current element. Okay, so this function takes the given array and the current value. It will return the index of immediate next of current. And here I'm going to set list dot set. I'm going to update at index with the current value, and at the end here I will return the length of the list. So list dot size. The size of the list is the longest increasing subsequence. Here actually we have to patch. Here we have to pass the list, not the nums. In the list we'll find out the immediate next of current. So list. Now let's call a function binary search. Binary search. This function takes a list and current. Okay, current, let's call it val right here. So let's call it val. Now let's declare two pointers, left and right. Left will point to the first element and right will point to the last element. Right equals to the index of plus statement list dot size -1. Now let's run a while loop here. While left is less than right, we'll keep run this loop. Now let's find out the middle. We can use here left plus right divided 2. Instead I'm going to use this formula, left plus right minus left divided by 2. This formula will overcome the overflow. Now if the value is greater than the middle value, if the value is greater than the middle value, list dot get mid, then we will shift left to middle plus 1. This is your binary search algorithm. Otherwise, else we will shift right to middle, and at the end of this while loop we will return the right. This is your binary search algorithm. This algorithm will take of in log n time complexity and the space complexity, the space complexity for the worst case of n. Hope you have understood how to solve this problem efficiently. This is the efficient solution of this algorithm. Thanks for watching this video.